Vectors. Let us revise scalars and vectors. A physical quantity which has magnitude only is called a scalar quantity. For example, volume, temperature, etc. A physical quantity which has magnitude as well as direction is called a vector quantity. For example, velocity, force, acceleration, etc. Vectors are usually denoted by p bar, f bar, a bar, ab bar, etc. and their magnitudes by mod of p bar, mod of f bar, mod of a bar, mod of ab bar, or simply p, f, a, ab respectively. A vector whose magnitude is 0 is called the zero vector or the null vector. It is denoted by 0 bar. A vector whose magnitude is 1 is called a unit vector. If E bar is the unit vector in the direction of the vector A bar, then E bar equal to A bar upon A, where A is the magnitude of the vector A bar. The unit vector in the direction of vector A bar is also denoted by A cap. Two vectors are said to be equal if they have the same magnitude and they are in the same direction. A vector having the same magnitude as that of a given vector A bar and the direction opposite to A bar is called negative of a vector A bar and is denoted by minus A bar. Two or more vectors are said to be collinear if their directions are same or opposite, irrespective of their magnitudes. Such vectors represent parallel lines, hence they are called parallel vectors. The vectors having same direction are called like vectors, and the vectors having opposite directions are called unlike vectors. A set of vectors which lie in the same plane or in parallel planes are called coplanar vectors. The vectors which are not coplanar are called non-coplanar vectors. Algebra of vectors. First, addition of vectors. Let A bar and B bar be two non-zero vectors representing OA bar and AB bar respectively. Then the vector OB bar is said to represent the sum of the vectors A bar and B bar, that is OB bar equal to OA bar plus AB bar equal to A bar plus B bar. This is called triangle law of addition of vectors. Second, parallelogram law of vectors. Let A bar and B bar be two non-zero vectors represented by OA bar and OB bar respectively. Complete the parallelogram OACB. Then the diagonal OC bar is said to represent the sum of the vectors A bar and B bar. If OC bar equal to C bar, then OA bar plus OB bar equal to OC bar, that is A bar plus B bar equal to C bar. Thus, parallelogram law of vectors can be stated as: the sum of two vectors OA bar and OB bar is represented in magnitude and direction by the diagonal of the parallelogram through O, of which OA and OB are adjacent sides. Scalar multiplication. Let A bar be a vector and M be a real number. Then MA bar is a vector which is called scalar multiple of A bar. If M greater than 0, then MA bar is in the same direction as that of A bar and has magnitude MA. If M equal to 0, then MA bar is a zero vector. If M less than 0, then MA bar is in the direction opposite to A bar and has magnitude minus MA. Properties of vector addition and scalar multiplication are: let A bar, B bar, C bar be the vectors and M, N are scalars. Then A bar plus B bar equal to B bar plus A bar. This is commutative law. A bar plus B bar plus C bar equal to A bar plus B bar plus C bar. This is associative law. A bar plus 0 bar equal to 0 bar plus A bar equal to A bar. A bar plus minus A bar equal to minus A bar plus A bar equal to 0 bar. M in bracket A bar plus B bar bracket complete equal to MA bar plus MB bar. M plus N in bracket complete A bar equal to MA bar plus NA bar. M in bracket NA bar equal to N in bracket MA bar equal to MN A bar. Position vector of a point. Let O be a fixed point and P be any point. Then the vector OP bar is called the position vector of the point P with respect to the fixed point O. This is generally denoted by P bar. If A bar and B bar be the position vectors of A and B with respect to fixed point O respectively, then AB bar equal to B bar minus A bar. Similarly, PQ bar equal to Q bar minus P bar, CD bar equal to D bar minus C bar, etc. If P is x, y, z, then position vector of the point P with respect to the origin O is given by P bar equal to OP bar equal to xi bar plus yj bar plus zk bar, and mod of OP bar equal to root of x square plus y square plus z square. If A bar equal to A1I bar plus A2J bar plus A3K bar and B bar equal to B1I bar plus B2J bar plus B3K bar, then A bar plus B bar equal to A1 plus B1I bar plus A2 plus B2J bar plus A3 plus B3K bar, and A bar minus B bar equal to A1 minus B1I bar plus A2 minus B2J bar plus A3 minus B3K bar. Scalar product of two vectors. If A bar and B bar are two vectors inclined at an angle theta, then their scalar product denoted by A bar dot B bar is defined as A bar dot B bar equal to AB cos theta. If A bar equal to A1I bar plus A2J bar plus A3K bar, B bar equal to B1I bar plus B2J bar plus B3K bar, then number 1, A bar dot B bar equal to A1 B1 plus A2 B2 plus A3 B3, that is product of components of I bar plus product of components of J bar plus product of components of K bar. A bar dot B bar equal to B bar dot A bar, that is dot product is commutative. A bar dot A bar equal to A square, therefore A equal to root of A bar dot A bar. Angle theta between A bar and B bar is given by cos theta equal to A bar dot B bar upon AB. If A bar is perpendicular to B bar, then A bar dot B bar equal to 0. This is the test for perpendicularity of two vectors. Projection of A bar on B bar equal to A bar dot B bar upon B. Similarly, projection of B bar on the line of A bar equal to A bar dot B bar upon A. This is the geometrical interpretation of dot product, that is A bar dot B bar equal to A in bracket projection of B bar on the line of A bar, that is B in bracket projection of A bar on the line of B bar. Scalar product is distributive, that is A bar dot in bracket B bar plus C bar equal to A bar dot B bar plus A bar dot C bar. A bar dot A bar equal to 1 if A bar is the unit vector. Vector product of two vectors. Vector product of two vectors A bar and B bar which are inclined at an angle theta is denoted by A bar cross B bar and is defined as A bar cross B bar equal to AB sin theta n bar, where n bar is the unit vector perpendicular to both A bar and B bar, such that A bar, B bar and n bar form a right-handed triplet. As cross is used to denote this product, vector product is also called as cross product. Important results. A bar cross B bar equal to minus B bar cross A bar. But mod of A bar cross B bar equal to mod of B bar cross A bar. Clearly, cross product is not commutative. If A bar and B bar are non-zero vectors and A bar cross B bar equal to 0 bar, then A bar is collinear, that is parallel to B bar. A bar cross A bar equal to 0 bar. As mod of A bar cross B bar equal to AB sin theta equal to mod of A bar cross B bar upon AB. There are two unit vectors perpendicular to the plane containing both A bar and B bar. They are plus minus A bar cross B bar upon mod of A bar cross B bar. I bar, J bar, K bar are unit vectors in the positive directions of X, Y and Z axis respectively. I bar cross I bar equal to J bar cross J bar equal to K bar cross K bar equal to 0 bar. I bar cross J bar equal to K bar. J bar cross I bar equal to minus K bar. J bar cross K bar equal to I bar. K bar cross J bar equal to minus I bar. K bar cross I bar equal to J bar. I bar cross K bar equal to minus J bar. If A bar equal to A1 I bar plus A2 J bar plus A3 K bar and B bar equal to B1 I bar plus B2 J bar plus B3 K bar, then A bar cross B bar is determinant. First row I bar J bar K bar, second row A1 A2 A3 and third row B1 B2 B3. If A bar and B bar represent the adjacent sides of a parallelogram, then the vector area of this parallelogram is A bar cross B bar. This is the geometrical interpretation of cross product. The area of this parallelogram is mod of A bar cross B bar. If A bar and B bar represent the diagonals of a parallelogram, then its area is half mod of A bar cross B bar. If A bar, B bar, C bar are the position vectors of the vertices A, B, C respectively of triangle ABC, then the vector area of triangle ABC equal to half in bracket A bar cross B bar plus B bar cross C bar plus C bar cross A bar. Vector area of triangle ABC equal to half AB bar cross AC bar. Therefore, area of triangle ABC equal to half mod of AB bar cross AC bar. The two products dot and cross are related by A bar cross B bar bracket square equal to A square B square minus square of dot product A bar dot B bar. This is called as Lagrange's identity. Collinear vectors. Two or more vectors are said to be collinear if their directions are same or opposite, irrespective of their magnitudes. Such vectors represent parallel lines, hence they are also called parallel vectors. Naturally, two vectors will be non-collinear if they are not collinear, that is parallel vectors. Condition of collinearity of two vectors. Two vectors a bar and b bar are collinear if and only if there exists a non-zero scalar m such that a bar equal to m b bar. Coplanar vectors. Let a bar and b bar be two vectors and x, y be any real numbers. Then the vector xa bar plus yb bar is called the linear combination of the vectors a bar and b bar. For example, 2a bar plus 3b bar minus half a bar plus 13b bar are linear combinations of the vectors a bar and b bar. We can extend this idea to more than two vectors. Thus, the vector xa bar plus yb bar plus zc bar, where x, y, z are real numbers, is a linear combination of the vectors a bar, b bar and c bar. The vector xa bar plus yb bar plus zc bar plus ud bar, where x, y, z, u are real numbers, is a linear combination of the vectors a bar, b bar, c bar and d bar. A set of vectors which lie in the same plane or in parallel planes are called coplanar vectors. The vectors which are not coplanar are called non-coplanar vectors. Clearly, two vectors are always coplanar. Three or more vectors may or may not be coplanar. Conditions for coplanarity of three or more vectors are given in the following theorems. Number 1. If a bar and b bar are any two non-zero non-collinear vectors, then any vector r bar coplanar with them can be uniquely expressed as a linear combination of a bar and b bar. From this theorem, it follows that if a bar, b bar, c bar are coplanar vectors, then any one of them can be expressed as a linear combination of the remaining two. Second, three non-zero vectors a bar, b bar, c bar are coplanar if and only if there exist scalars x, y, z, not all zero simultaneously, such that xa bar plus yb bar plus zc bar equal to 0 bar. Number 3. If a bar, b bar and c bar are three non-zero non-coplanar vectors, then any vector r bar in the space can be uniquely expressed as a linear combination xa bar plus yb bar plus zc bar, where x, y, z are scalars. Using this theorem, we can obtain position vector of the point P, x, y, z in the space as OP bar equal to xi bar plus yj bar plus zk bar, where I bar, j bar and k bar are unit vectors in the positive directions of coordinate axes x, y and z respectively. Section formulae. Internal division. If the point P lies on segment AB, then it is said to divide segment AB internally in the ratio AP is to PB. The position vector of the point P, which divides segment AB internally in the ratio m is to n, where a bar and b bar are the position vectors of the points A and B respectively, is given by r bar equal to mb bar plus na bar upon m plus n. This is called the section formula for internal division. Its corollaries are midpoint formula. If pxyz is the midpoint of the segment AB, then position vector of the midpoint is given by r bar equal to a bar plus b bar upon 2. Centroid formula. If g bar is the position vector of the centroid G of triangle ABC, then g bar equal to a bar plus b bar plus c bar upon 3, where a bar, b bar, c bar are the position vectors of the vertices a, b and c of triangle ABC respectively. External division. If the point P does not lie on segment AB but lies on line AB, then it is said to divide segment AB externally in the ratio AP is to PB. The position vector of the point P, which divides segment AB externally in the ratio m is to n, where a bar and b bar are the position vectors of the points A and B respectively, is given by r bar equal to mb bar minus na bar upon m minus n. Scalar triple product. Consider the vectors a bar, b bar, c bar. We know that b bar cross c bar is a vector, so we can form the product a bar dot b bar cross c bar. This product is a scalar and is called scalar triple product of the vectors a bar, b bar, c bar. The scalar triple product a bar dot b bar cross c bar is also denoted by a bar, b bar, c bar and is called the box product. If a bar equal to a1 I bar plus a2 j bar plus a3 k bar, b bar equal to b1 I bar plus b2 j bar plus b3 k bar, and c bar equal to c1 I bar plus c2 j bar plus c3 k bar, then the box product a bar dot b bar cross c bar equal to determinant a1 a2 a3, b1 b2 b3, c1 c2 c3. The properties of scalar triple product are: number 1, if positions of any two vectors in a scalar triple product are interchanged, scalar triple product changes in sign only. That is, a bar dot b bar cross c bar equal to minus b bar dot a bar cross c bar. Second, the cyclic changes in the positions of vectors a bar, b bar, c bar in the scalar triple product are allowed. That is, a bar dot b bar cross c bar equal to b bar dot c bar cross a bar equal to c bar dot a bar cross b bar. The positions of dot and cross in a scalar triple product can be interchanged without changing the equality. That is, a bar dot b bar cross c bar equal to a bar cross b bar dot c bar. If b bar and c bar are collinear, then b bar cross c bar equal to 0 bar. Therefore, a bar dot b bar cross c bar equal to a bar dot 0 bar equal to 0. Thus, if in a scalar triple product any two vectors are collinear or equal, then the scalar triple product is 0. If a bar, b bar, c bar are coplanar, then a bar dot b bar cross c bar equal to 0. This is because b bar cross c bar is a vector perpendicular to the plane of b bar and c bar. Hence, if a bar, b bar, c bar are coplanar, then b bar cross c bar is also perpendicular to a bar, and the dot product of two perpendicular vectors is 0. Hence, a bar dot b bar cross c bar equal to 0. Geometrical interpretation of the scalar triple product. If a bar, b bar, c bar represent the coterminous edges of a parallelepiped, then the box product a bar dot b bar cross c bar represents the volume of the parallelepiped. Remarks. Number 1. If a bar, b bar, c bar are coplanar, then the volume of the parallelepiped is 0. Hence, we can say that the three vectors a bar, b bar, c bar are coplanar if their box product equal to 0. Second, if 4 points a, b, c and d are coplanar, then the three vectors AB bar, AC bar, AD bar are coplanar. Hence, the box product AB bar dot AC bar cross AD bar equal to 0. Number 3. If A bar, B bar, C bar represent coterminous edges of a tetrahedron, then its volume is 1 upon 6 the box product A bar dot B bar cross C bar. Applications of vectors. Using vectors we can prove the following. Number 1. Medians of a triangle are concurrent. Number 2. Bisectors of the angles of a triangle are concurrent. Number 3. The diagonals of a parallelogram bisect each other, and conversely, if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Number 4. The median of a trapezium is parallel to the parallel sides of trapezium, and its length is half of the sum of the lengths of the parallel sides. Number 5. Altitudes of a triangle are concurrent. Number 6. The angle subtended by a diameter of a circle at any point on the semicircle is a right angle. That is, angle inscribed in a semicircle is a right angle. Number 7. In triangle ABC, O is the circumcenter and H is the orthocenter. Then H bar equal to A bar plus B bar plus C bar, where H bar, A bar, B bar and C bar are the position vectors of the points H, A, B and C respectively with respect to the origin O. 8. The diagonals of a rhombus bisect each other at right angles. 9. The segment joining the midpoints of the diagonals of a trapezium is parallel to the parallel sides and equals half its difference. 10. The midpoint of the hypotenuse of a right angle triangle is equidistant from the vertices. 11. The perpendicular bisectors of the sides of a triangle are concurrent. 12. The diagonals of a parallelogram are congruent, then it is a rectangle. 13. The sum of the squares of the diagonals of a parallelogram is equal to sum of the squares of its sides. 14. If two pairs of opposite edges of a tetrahedron are orthogonal, then the third pair is also orthogonal. 15. The parallelograms based on the same base and between same parallel lines are equal in area. 16. If the lengths of the two non-parallel sides of a trapezium are equal, then the lengths of their diagonals are also equal. 17. With usual notation for a triangle ABC, cos A equal to B square plus C square minus A square upon 2BC. This is cosine rule. 18. In any triangle ABC, with usual notation, C equal to A cos B plus B cos A. This is called as projection rule. 19. Cos of alpha minus beta equal to cos alpha cos beta plus sin alpha sin beta. 20. Cos of alpha plus beta equal to cos alpha cos beta minus sin alpha sin beta. 21. Sin of alpha plus beta equal to sin alpha cos beta plus cos alpha sin beta. 22. Sin of alpha minus beta equal to sin alpha cos beta minus cos alpha sin beta. 23. With usual notation in triangle ABC, sin A upon A equal to sin B upon B equal to sin C upon C. This is called as sine rule. The concept of direction cosines and direction ratios. Let L be a line in space. Take a line OP through O and parallel to the line L. Let us rotate the ray OX, that is the positive x-axis, in the anticlockwise direction till it lies along the line OP. Then we get a directed angle. This angle is called the angle made by the line OP with the positive direction of the x-axis. If alpha, beta, gamma are the angles made by the line OP with the positive directions of x, y and z axis respectively, then the line L is also said to make these angles with the positive directions of the coordinate axis. These angles are called the direction angles of the line L, and the cosines of these angles, that is cos alpha, cos beta, cos gamma, are called the direction cosines of the line L. From the above it is clear that parallel lines have the same direction cosines. Also, 0 degree less than or equal to alpha less than 180 degrees, 0 degree less than or equal to beta less than 180 degrees, 0 degree less than or equal to gamma less than 180 degrees. The direction angles of the x-axis are 0 degree, 90 degrees and 90 degrees. Hence, the direction cosines of the x-axis or any line parallel to it are cos 0 degree, cos 90 degrees and cos 90 degrees, that is 1, 0, 0. The direction angles of the y-axis are 90 degrees, 0 degree and 90 degrees. Hence, the direction cosines of the y-axis or any line parallel to it are 0, 1, 0. The direction angles of the z-axis are 90 degrees, 90 degrees and 0 degree. Hence, the direction cosines of the z-axis are 0, 0, 1. If alpha, beta, gamma are the direction angles made by a line with x, y and z axis respectively, then cos square alpha plus cos square beta plus cos square gamma equal to 1. From this we can derive cos 2 alpha plus cos 2 beta plus cos 2 gamma plus 1 equal to 0. That is sin square alpha plus sin square beta plus sin square gamma equal to 2. Direction ratios. If LMN are the direction cosines of a line and the numbers A, B, C are proportional to LMN, then ABC are called direction ratios or direction numbers or direction proportionals of the line. Let ABC be the direction ratios of a line whose direction cosines are LMN. Then L equal to plus minus A upon root of A square plus B square plus C square, M equal to plus minus B upon root of A square plus B square plus C square, and N equal to plus minus C upon root of A square plus B square plus C square. If P is x1, y1, z1 and Q is x2, y2, z2, then the line PQ has direction ratios x2 minus x1, y2 minus y1 and z2 minus z1. Clearly, the components of a vector are direction ratios of a line along that vector, and components of a unit vector are direction cosines of that line along the vector. Angle between two lines. The acute angle theta between the two lines with direction cosines L1 M1 N1 and L2 M2 N2 is given by cos theta equal to mod of L1 L2 plus M1 M2 plus N1 N2. If A1 B1 C1 and A2 B2 C2 are the direction ratios of two lines, and if theta is the angle between them, then cos theta equal to A1 A2 plus B1 B2 plus C1 C2 upon root of A1 square plus B1 square plus C1 square into root of A2 square plus B2 square plus C2 square. Clearly, for perpendicular lines, L1 L2 plus M1 M2 plus N1 N2 equal to 0, that is A1 A2 plus B1 B2 plus C1 C2 equal to 0. If two lines are parallel, their direction cosines are equal and their direction ratios are proportional. If θ1, θ2 and θ3 are the angles made by the line OP with the planes XOY, YOZ and ZOX respectively, then cos square θ1 plus cos square θ2 plus cos square θ3 equal to 2, that is cos 2 θ1 plus cos 2 θ2 plus cos 2 θ3 equal to 1. The measure of the angle between any two diagonals of a cube is cos inverse 1 upon 3.